Okay, so today it is going to be talking all about the derivative. This is probably the first, what I would call the first real thing in calculus, as in something that we're really getting to the core of what calc is all about. We've done the limits, but now we're going to start applying some of these things. And the good news I'm going to tell you, what I tell all my calc students, pre-calc students, is calculus isn't difficult. I might have said this in the beginning. It's all about the algebra. So I'm going to show different things today, and the actual calculus concepts are not difficult at all. They're just normal, easy steps, but it's all the algebra that's going to be associated with it. We're going to have to simplify. We're going to have to solve, clean up, cancel, factor, all those old things come into play. That's what makes these problems difficult. But the actual steps I'm going to show you, they're really not as ugly. It's just a matter of getting it all finalized here. Okay, so like always, I'm going to go through the slides here and just kind of show you some things. Before I pop into that one, I wanted to point out one other thing. If you can see on my screen here, when you go into your class, all these PowerPoints that I use for these lectures, remember they're all here. You may have different things listed here, but if you click on this Multimedia Library, and for example, click the chapter, we're in Chapter 2, Section 4, and then the big thing is if you do find out nothing happens, you have to select all or select PowerPoint. But when you select them and now find them, get all these videos, and here's the PowerPoint that I'm using. So if you ever want to go back and look at the slides without all my writing on it or any of that stuff and just see kind of the raw version, you can always download it or view it here at this spot. Okay? So that being said, let's get right into this particular PowerPoint, talking about what the derivative is. Okay, so here, concepts of limits help you solve. Okay, got all that. We've done our limits enough. And here's what it's going to come down to. We're going to find what is called this tangent line. It's a very important line. It's the most important line because it tells so much about the behavior of your graph. Because we're going to have functions that are bouncing up and down, going up to infinity, crossing over the x-axis, all these things. This tangent line is a special line that hits our graph at exactly one point. So it doesn't go through your graph like that. It doesn't miss the graph. It hits it right there. It kind of bounces off. And the key is it's at that perfect moment where you can almost, it's not a great one, but it's like a 90-degree angle and you kind of have a little symmetry on both sides. Okay? It's at one spot. Now I compare it to, you can't really see me doing this, but if I had a pencil, or sorry, let's do this. Pretend this is a hill and a car is driving. At any point, the car is facing different directions, up and down by the slope. So when the car is over here, the car is pointing downward. Then as it gets to the bottom, it's sort of facing flat. Then it starts climbing up. And the angle of the car is what we care about because that's going to associate to the tangent line. So when the car is right here, this line sort of represents its angle. Okay, it's where it's going. Like I said, it touches it at exactly one spot. So as you start moving over, here's a tangent line at this spot. Here's a tangent line at that spot. And then over here, there's a tangent line over here. There's a bunch of tangent lines throughout your graph. Our job is we need to figure out what these are because the behaviors of these lines tell you the behavior of your graph. And it's things like increasing, decreasing, where are the high points? Where are the low points? Where are the middle grounds? All these things, we're going to use the derivative to figure it out. Okay, so one thing we're going to be doing is we're going to see a graph like this, and they're going to give us a point. They're going to say, go find the equation of that tangent line right there, that red line. Okay, another thing we're going to do is we're going to find instantaneous velocity, and that's an interesting one because if you ever, like this case, this example, we'll see this in a couple slides. When you drop something off of a building, if you've done this before, it starts off slow the moment you drop it, and gravity starts pulling on it, and it gets faster and faster and faster until it hits the ground. At any one point, it's like we want to freeze time or say, right there, get a radar gun and take the speed. That's the instantaneous velocity at any given point. But it varies because it depends on how far away are you from the ground, how far away from when you dropped it. So all of these things we're going to learn are going to help us give these answers. Okay? So start off a few things here and kind of examples that may work for you. You pass mile marker 120 on the interstate highway at 9 a.m. You pass mile marker 250 at 11 a.m. Now, again, if you're not familiar, every mile there's a mile marker. So we've basically gone 130 miles in 2 hours. And the question is, what's the average rate of change of distance with respect to time? And more importantly, it's at average velocity. What's the average speed you're going? Now, you've all been on trips before. It may take you 2 hours to go the 130 miles, but during that 2-hour time span, you might have been going fast, you might have been stuck behind a truck, you might have almost stopped. But overall, the average speed is what we're going to figure out. So that's what we're looking for. And the formula is an old one, if you remember. The distance equals rate over time, or in this case, when you're looking for velocity, and just so we're clear, velocity is pretty much the same as your speed as your rate. Velocity, though, you'll see later on, it does have a component of what direction are you going. So going 50 miles an hour to the east is technically a different velocity than 50 miles to the west. For the most part, though, I just want you guys to think of it as speed. Okay, you can get away with that, you'll be okay. So when we're looking for a speed, which is the same as a rate, okay, like I said, it's not exactly, but it's for our purposes, the formula is the distance over time. How much distance did you travel over what time span? So the formula, they don't really put a formula here, but if you look at it, it's sort of like this old formula you use to get your slope. You're going to subtract how far did I travel, and you're going to subtract the times, and that's how we get our 2 hours here, which you already knew by looking at this. You knew this is going to be 2 hours, but this is the actual formula. You subtract what time is it now, subtract off what time it was when you started. That's how you get the 2 hours. And same with the miles. We're at mile marker number 250. Subtract where it was when I began this, and I was at 120. So the difference is how far I traveled, in this case 130 miles. So you divide those two, and what it's saying is you went an average of 65 miles per hour. That's the average velocity. That's what you're going to need to find. Okay? And like I said earlier, it's going to vary faster or slower, and this is going to tell you exactly how fast, your average, not exactly, your average speed over that. So here's the formula, kind of like that y2 minus y1. You're going to subtract the a values. Now, the terminology is a little bit weird, but I'll tell you, you're starting at a, and then you're ending at a plus h. So kind of think of a road right here. Here's a, here's a plus h. The difference is h. It's just a fancy way to say h. How far do we travel? We travel h meters or miles or feet. That's why it ends up h down here at the bottom of this formula. How far did you, did you go when you're finding these two things out? What was the average rate of change? So we're going to plug in our x values down there, and then this is the corresponding y values on top. The y value of this x, y value of that x. Again, that's like that y2 minus y1 over x2 minus x1. It's just a different way to look at this, though. Okay, but like the last problem, we're just going to subtract them all and see what we get and simplify your answer. Now, obviously, h cannot be 0 for the reason of you can't have a 0 on the bottom, but mainly because if h was 0, that picture I just erased, that means you traveled 0 amount. You didn't move at all, so there will be no average rate of change. You can't measure it if you don't move. Okay, so this is called the difference quotient. We had this before. Notice how that does look familiar. We had to subtract it. You had to plug in the a. You had to plug in the a plus h. We're going to use this formula. That's why they brought it up before, because this is going to come into play this entire section of the book here. Okay, so now we get a company. They make plastic planter boxes. The revenue is given by this formula, and it only applies when x is between 0 and 1,000. They want to find the change in revenue production if production changes from 100 planters to 400 planters. Okay, so remember, you were at 100, you go down to 400, you're not down, you increase to 400. They want to know what's the revenue going to change. So I can see right now we're increasing by 300, but we want to figure out how much also. In this case, they're not asking what the difference of the planters is. They're asking what's the difference in the revenue. So you got to go figure out what's the revenue at 400 and what's the revenue at 1,000. Okay? Now remember, this is the ending amount. What you finish at, this is what you started. Okay, if I go back a couple slides, remember that 9 a.m. or the markers, we ended at 250. we began at 120, so we always take the end number, which is 250, and subtract where we started, the 120. That's how we got the 130. Same with the times. The ending time was 11. You subtract the starting time, 9, from that. So that's why they did it this way. All right, so now in the formula, you plug in the 400 and you get this. And it's not 100% clear, so I'll make sure to highlight it. This is from plugging in the 400. This is plugging in the 100, so you figure out both sides. You get 4,800 revenue when you have 400 units, planters, 1,800 when you have 100 planters, so the difference is 3,000, and that was the question. They asked, what was the change in revenue? So make sure you answer the question. They didn't say, what was the change in planters? Then you would say 400 minus 100, but their question was, what was the revenue change? So you need to figure out what was the old revenue, what was the new revenue, and how much different was it, and that's our answer here. Okay? So now, revenue is increased by 3,000 when the planters increased from 100 to 400. Now they want to find the average rate of change. Okay, so we already know it's going to be 3,000, and the change in production is 3,000, and here's that same formula. Remember, this is the end right here. This is the start. So we subtract the x's on the bottom, we subtract the corresponding y values on the top, and then that's how we get the 3,000 on top, the 300 on the bottom. So what happened is, it changed by 3,000, but your production also went up. What they want to see is basically, what was the average rate of changes? Well, we went up, we made an extra $10 is what's going on. We're making more here. So that's our average rate of change. Okay, so looks like it's the same. Oh, here's the graph of the same problem. Okay, so here's your graph of r of x equals 20x minus 0.02x squared. The graph is the revenue function, and you see there's the 100 and the 400. They didn't make it very clear, but here's the 100 right here. Here's the 400. So what happened was, between these two, it went up 3,000, and the units went up 300, and basically, why that looked like a slope formula? Because that's what we are finding here. The average rate of change is basically, what's the slope, what's the direct path to the two? Okay, now this is important because you see how production goes, or revenue goes up, then at some point, notice over here, the revenue is going to start to drop. That was the thing we talked about before. When you start making too many, you're not making the revenue because you're not selling enough. And it's kind of, I'll show you an interesting example here. If I look at what happens from 100 to, I think that's 900 right here, and I draw the line straight over, it's going to be a big zero because even though we increased a bunch right there, our our revenue didn't move up at all. So the difference of the revenue on the top, the f of 900 minus the f of 100, or r of 900 minus r of 100 is going to be the same. They're going to be 0, so we're going to get 0 over 800. That's why it's a 0, and notice that's the slope of that line right there, that horizontal line. So pick any 2 points on your graph. I can go from here to here. If I want to know the average revenue, okay, remember the question from here before, the average rate of change of revenue? It's basically, what's the slope connecting the start and the finish? What's the slope of that line? And a lot of what we're doing in this section is all about, can you find the slope? Can you find the equation of a line? Can you work with all those? So again, they're just sort of pointing out what's going on. The secant line is what it's called. Now, a secant line is basically any line that connects 2 different points of a graph. Any function you have, like the examples I was showing, just take 2 dots, connect them. That's the secant line. So what we're doing is we're finding the slope of that secant line right there, whatever that may be. Okay, so now we talk about a steel ball being dropped from a tower. Now, if you remember your basic science and physics, it doesn't matter how much the ball weighs. All right, for the most part, aside from getting draft from a feather or a kite or a sail, a parachute, everything will drop the same. So I can have a 10-pound brick or I can have a 1-pound steel ball. They're going to fall at the same rate. So we don't care about the speed of we don't care about the weight of the ball. We just care about where it's dropped from and how much. So the formula is And make sure as you start seeing more of these formulas, know what the variables stand for, okay? It's y is the number of feet. That's how far the ball is going to fall, the y, which is up and down, like you know. And then the x represents how many seconds have passed. So if you think about it, when I first plug in 0, that's the moment I let the ball go. If I plug 0 into this formula, my y is 0, and that makes sense because if 0 seconds have passed, 0 feet, your ball's dropped. But if I put 1 in for x, so 1 second, you plug it in there, you get 1 squared is 1 times 16 is 16. That means the still ball will have dropped 16 feet in the first second. And you notice because it's a square, as you start plugging in bigger numbers, like if I plug in 5, I get 5 squared, which is 25 times 16. It gives me a 400. In 1 second, we go 16 feet. In 5 seconds, we go 400 feet. This is kind of like an exponential graph, but it's going to be a parabola. But you're going to get an increase in the distance the longer it's dropped because, again, gravity is making it increase its speed, so it's covering more distance. So you look at what's going on, and I kind of like these pictures so you can see it here. It doesn't have to be the Leaning Tower of Pisa. It's just any kind of a tower. They do that just so you can see it, the ball falling clean off. But you see what happens. At 1 second, at 0 seconds, it starts at the top. At 1 second, it's down to 16 right here. In 2 seconds, it's down to 64. And at 3 seconds, it's all the way to 144. You see how the gap is getting bigger and bigger? Because it's picking up speed because of gravity. Okay, now the good news is all of it is contained in that formula. So if you understand how to just plug in numbers of the formula, you're going to get it. What you have to remember is y is this distance right here. How far did I go down from that top spot? That's the y value that you're calculating, the f of x that you're plugging in and you're getting a result. The number you get is how far it's fallen. Okay. So now we have the formula, and they want us to find the average velocity from 2 to 3 seconds. Now go back to this picture. You're going to see that ball is picking up speed. And it isn't like it's going a certain speed, then it hits 1 second, and it picks up, and it jumps to a new speed, then it jumps to a new speed. It's like you driving a car. As you put your foot on the gas, your speed starts increasing. And if you had a radar gun, or if you look at your speedometer, it goes up and up, especially if you have a digital one. You see it increasing speed. It may go up fast, but it's increasing. What you never see is you won't see your car go from 5 and jump all the way to 20 instantaneously. It's got to hit 6, 7, 8, 9, 10, 11, all the way up to 20. It may go very fast, but every speed is attained. So it's constantly increasing speed here as it's falling downward. So they're asking between 2 and 3 seconds, what's the average speed? So we know it's going to be fastest down here, and we know it's going to be the slowest in that range right there. But what's the average? And it's not necessarily just the difference in subtract, or take a speedometer and look at the two and take the average. You have to follow the formula that we did earlier. So remember the formula. You're going to find f of 3 and f of 2, and then you're going to subtract those. And on the bottom, you're going to also find the difference of the 3 and the 2. Okay, so this is kind of the same thing we talked about earlier. The distance over time is going to be your rate, your speed. So the distance covered, and you see there's where our formula pops up again. We take f of 3 minus f of 2. And remember, 3 is the ending time. It goes 1, 2, 3. 3 is the finish time. So at 3 seconds, f of 3 minus f of 2 divided by 3 minus 2. Plug those both into the formula, and you'll see that it's traveled 80 feet. Go back to that picture again. The difference right there, and you can even see it, this is 80 feet. 144 minus 64, and how long did it take? It took 1 second. Now, if you didn't have this picture, you can still figure it all out doing exactly this. F of 3 minus f of 2, all over 3 minus 2. That right there is going to give us our average velocity, the same formula that I started with, and that's how we get, the 80 feet per second. Okay, so now same kind of thing here. They want you to find and simplify the average rate of change from x equals 2 to x equals 2 plus h. All right, so what's going on is h is going to be a new variable that we're going to introduce. And we're going to have to figure out what happens, because h could be 1, so it's going to be a total of 1 second has passed, or it could be 5, Another 5 seconds has passed, but h is going to be our new variable. So what we're going to do is the same thing. We have our same formula, and remember, you're starting at x equals 2, you're ending at x equals 2 plus h. So remember the same thing? You start, your finish time is 2 plus h, so we have that there, and we subtract the beginning time. On the bottom, we have the 2 plus h, and we subtract the starting time of 2. That's why you get a plain h down there. The 2's cancel off, because h is how far you've gone. So unlike the last example, because I'm plugging, I'll be okay with f of 2, but the f of 2 plus h, when you plug in a variable to a function, you're not going to get a clean number, and we get all of this. And so you see where that comes from. F of x equals 16x squared. Well, we want to find f of 2 plus h. So I replace every x with a 2 plus h. And just to show you where it all comes from, remember when you have a parenthesis squared, it means multiply the parenthesis times itself. So we have to FOIL it, and we get this. Then when you distribute, that's where the 64 plus 64h plus 16h squared came from. So again, this PowerPoint slide doesn't show every little step. That's how you get that first part. Okay, so that is what equals this part. Then we have to go find f of 2. Well, not a big deal. We've done this already, but here's our formula. If I want to find f of 2, I just plug that in, and I found f of 2 is 64. So that is replaced with the 64 right there. Okay, so pause this video if you need and kind of look at both sides of this, make sure you understand where those two pieces come from. And now, what they've done is they've simplified it. So the 64 is canceled off. So on the top, I have a 64h plus 16h squared. They factor out the h. So that's why there's an h parentheses 64 plus 16h. And then the h's cancel off, so you're left with just this right here. So what that's saying is, this is my formula for the average velocity. I don't have an answer, but I know that if you start at 2 seconds and you go to any number after 2, I can learn what the h is, I can plug it into here, and I will be able to get right to the average velocity. Okay, and I can plug in anything and get whatever answer it's going to be. All right, so that's how you're going to find this, and you're going to use this x plus h, this 2 plus h. You're going to have to go plug that into the function a number of times on the homework coming up. This is going to be a regular occurrence, so I don't want to just say get used to it, but you got to get comfortable with it. You got to get used to it because it is going to happen. So my hope is that I'll do enough examples where you're going to see this and you're going to see what's going on. Okay, so same formula, same problem. They want you to find the limit of the general expression for the average velocity. And this is one of these where don't worry if this doesn't make any sense. They're going to give you this formula right now. I'll give it to you if they don't show it. And the average velocity we already found is going to be 64 minus 16h. Okay? So here's what happens. That is what we found given any kind of thing starting at 2. Okay? So what's going to happen is they want to know what happens as h approaches 0. So you see this formula. I can go plug in different numbers, 1, 2, 3, 4, 5, 6, and it's going to give me the exact number right there. They're saying what happens as h gets smaller and smaller and smaller. What happens? Well, all that means is, let's look at only this right here. Okay? That right there, we want to see what happens as h gets closer and closer to 0. Now, we already know you can't plug in 0 because of that h down there is going to give me a 0 on the bottom. However, from the last slide, the h canceled on the top, and now we're left with this. Once it cancels, now I can actually plug in 0 for h. So the 16h cancels, and I'm left with a limit of 64. And it tells me that's what's happening. Okay, that's what's going on as I'm getting closer and closer to the original number. All right, so let's get to an actual problem where you're going to see how this works. What are some possible interpretations of the limit of this average velocity? Okay, So this was at 2 seconds. If you go back to what we found a minute ago, remember, we started at x equals 2. And we said, okay, in fact, I'm going to go back to the tower so I can show you this visually here. They're saying at x equals 2, we are right here. And they're saying, let's go another h seconds. So if h was 1, we can go find the average velocity, and then remember that was the 80 in between these two. If h is bigger, it's going to get there. But what they're saying is make h get smaller and smaller and smaller. That means you're getting closer and closer to this starting point. Now, the first thing I was saying, remember, you can't have 0 time go off the clock, but let's make it the shortest possible time we can, like right there. Maybe make it where we're only going to go 0.1 seconds, and we want to measure what was the average rate of change between 2 and 2.1. And we can figure out that number, then we can do it again. Let's say it's 0.01, 0.0001, just like our limits before. What it's saying is we're getting closer and closer to 60. We're going to actually find the exact velocity when your ball is at 2 seconds. After it's gone 2 seconds, this formula will help us tell exactly what the speed was at 2. So it's essentially the same as if you have a system hooked up, a radar gun, and you release it and you have the computer automatically say, after 2 seconds have passed, hit the radar gun and see what the speed is. That's what we have just figured out right here. We figured out that the average velocity at 2 seconds is 64 feet per second. We can do that all without the radar gun just by looking at our formula. So here's what matters right here. This is the one that you need to write down. Have this on a piece of paper, have it nearby, have it next to your computer or whatever, because you're going to use this a lot on this first homework and probably the first quiz, and then some. So given any function, if you want to know the instantaneous rate of change at any given moment, like at that 2 seconds that I just talked about, but now it could be any time, 2, 3, 4, 5, whatever, 1. If you want to know the instant rate of change right there, it's this formula. It's the limit as h approaches 0 of f of a plus h minus f of a all over h. And they say if the limit exists, and that's what we're going to find out, but that's going to tell you the exact velocity. Okay? So, where this is going to come into play, and all is tied together. See that secant line right there, remember? At any point, a secant line it crosses through your graph in 2 spots. Okay? Now, what I want to find is the tangent line. Remember, that's the place that you touch the graph only in 1 point. So tangent line hits it once, secant line is going to hit it 2 different spots. We're trying to what we care most about is just the tangent line. Okay? So you're going to see what happens is, I can find the slope of that tangent line right now. You know this from algebra. If you give me the points P and Q, I can go find out the slope of that green line. But I want to find the slope of the red line. And the problem with the red line, if you just look at the red line, the only thing we know about the red line is it's tangent to the circle, okay, but we know it only touches 1 point. And from algebra, you can't get a slope unless you have 2 points. You need 2 points. But you see what happens as Q, they're not going to show it, but here's what I'm going to show it. If you read the left side here, they say as Q gets closer, so notice we can find this slope, no problem, but we want that slope. So just eyeballing it, I can tell they're not going to be the same. They're going to be off, I don't know by how much, but here's what I want to do. I want to move Q closer. So let's say the Q is right here. Now when I connect these dots, notice this line, I still have 2 points. I have P and Q. I can find the slope, and you notice my slope is starting to get closer to the red one. It was far away with the green. Now this black line is getting closer. Now let's say I do let's do an orange line. Let's say I make Q even closer right here. And I connect P and Q. Notice, still not the same as the red line, but I'm getting closer and closer and closer. As Q gets closer and closer to P, you're getting closer to the actual slope of the tangent line, and that's our goal here. So what we want to do is try to figure out, well, what happens as you get closer and closer? This formula is going to tell you that slope right here. Okay, that one, wait, where'd it go? So I go back right there. That's the one we're going to use. We're going to use that same formula here. So a line containing 2 points is the secant line. We talked about that. You can find the slope of that. And in this situation, we can find any slope between any two lines. There's your green line. There's your secant line. Okay? But what we want to do is we want to get the tangent line. So here's our formula. What it's saying is we want to get, and I'll go back and let me show you this. Remember, it's a slope is really what we're caring about. So let's go back to your old slope formula. As your x's get closer and closer and closer together, think about that. As I put x's closer and closer, they basically become a 0. Because when you get 5 minus 5, it's a 0. So what happened? That's why they're saying the limit as this number down here approaches 0. As these two numbers get closer and closer to 0, what's going on with the slope? Well, we can't plug it in. We can't calculate it that way. This is why we learn how to do limits in the last section. We can find the limit of this, and it's telling us what the behavior is, what it's going towards, and that's telling you what the slope will actually be of this tangent line. So we have this phrase right here, this whole expression. This is going to be known as, I'll write it down here, this is f prime of x. That's how you say it, okay? That is going to be what's known as your derivative, right there. F prime of x, it's going to be a whole new function. It's going to be something we're going to find very soon. This is the first method how we're going to find that given derivative, f prime of x. So you see that little hash mark between the f and the x? That's not a quote, that's not an apostrophe. Well, it's technically an apostrophe, but it doesn't mean possession. It is the symbol for derivative right there when you see that little hash mark. Okay, so when you see a function and they want you to find this, you need to use that formula right there. That's what we're going to be doing. So something is differentiable is if it exists. The process for finding the derivative is differentiation. Okay? And we're kind of using the same words, so don't get wrapped up on this. Don't get bothered by this. Yeah, differentiating is the actual act. It's just different parts of speech. So now we want to figure out how to find this. The new function is going to be called f prime. That's what that is on the right there. So the domain of the derivative, the f prime, remember it's a new function, it's going to be a subset of the original domain. What that means is whatever you found the domain to be of the function, the domain of the derivative is going to be either that or a little bit smaller, because sometimes points disappear, but you're never going to get points now that are in the domain of the derivative that were not in the original function. So it has to be from the domain of the original and then maybe smaller. That's why they say the subset. Okay, so we say the slope of the tangent line, which I've been referring to. This is going to be what the derivative is going to help us figure it out. And it's also going to get us that instantaneous rate of change or the velocity. It's going to do all these things. So here's the nice step-by-step process. This is another reason why I told you about these slides. Remember slide 18 if you download this, or take a screenshot of this, or write it down, because this is the step-by-step. So remember, and I know I'm going back and forth, that formula right there, that is what we're going to have to use. So this is the step-by-step process of what you have to do. First off, find f of x plus h. Then you're going to take what you just found and you're going to subtract f of x. And remember, f of x is just your original function. So take that difference, you're going to divide it by h, then you're going to find the limit as h approaches 0. And hopefully this will come out to be something you want. So here's our example. Now you can see it in action. We have the function negative 16x squared plus 80x plus 6. So remember, the first step, find f of x plus h. We do that by taking the original function and we replace every x with an x plus h. And my recommendation is just like it says here, every time you had an x, it becomes a parenthesis x plus h. So that we're clear, the parenthesis x plus h is what's being squared. The parenthesis x plus h is what's being multiplied by 80. And you're going to need to spend a step or two a lot of times to clean this up, to simplify this. So I FOIL out that first parenthesis, x plus h times x plus h. And let me do this over here on the side because I know a lot of students have issues with this. This part right here is what I'm working on, okay? It means x plus h times x plus h And trust me, you're going to do this so many times, it's going to make, you're going to know this without even trying in a little bit. But when we FOIL this out, we get x squared, we get an xh, we get another xh, and we get an h squared. And those two middle terms, that's why you get a 2 plus 2xh, I'm sorry, in the middle. Make sure these don't look like b's, I'm sorry. They're all h's. So that's how they got this right here. It was the FOILing out of the x plus h squared. So again, pause this if you need to go back and understand where I got that result from, why it's there. All from FOILing a parenthesis. When you have a parenthesis squared, it always means you need to break this down and FOIL it. Okay, so then we're just cleaning up. Remember, we're just finding f of x plus h. We're cleaning this up. We're distributing the negative 16. Make sure you know that's a negative that's distributing. So all these signs change. And now we just start combining, simplifying our terms. Oh, where'd it go? Okay. Oh, yeah, I guess I'm sorry. Go back. It was simplified. Sometimes you're going to be able to combine certain things. It looks like this. We just had 6 terms and none of them are similar. So we get a big expression here. But this entire thing right here, this is what's equal to f of x plus h. That's what we found. So when I'm going to take all of this and go to step 2, which says find f of x plus h minus f of x. Well, everything we just found goes right here. And then we take the function and we're going to subtract it right here. So look at this for a second. See what you get. F of x plus h is all of this. F of x is all of this. And don't forget you have to subtract it. That's why there's a parenthesis on that far right side. Okay, so the first one we don't really need a parenthesis, so we just simplify it. We drop that parenthesis. We distribute the negative through here. And this is why it's a plus 16x squared, a minus 80x, and a minus 6. And then we combine similar terms. And what's going to happen almost always is that you're going to get terms that are going to cancel off. So the 16x squared is going to cancel with the negative 16x squared. The negative 80h, or x, wrong one, sorry. The negative 80x cancels with the 80x. The negative 6 cancels with the positive 6. And after all that, you're left with a much smaller expression of just 3 terms. Okay? So that is f of x plus h minus f of x. That's phase 2, step 2 in our process. Your third step is you're going with this entire thing, you're going to divide it by h. So everything we just found, right here, all this stuff, we divide it by h. That's going to make things cancel off. And all you're doing is you're canceling h, one of them out of every term on top. If you did this right, every term should have an h on the top and everything cancels, so you should have nothing on the bottom. If you still have an h on the bottom, then you probably messed something up on one of the previous 2 steps. So now we're here, and the answer is, what's the limit as h approaches 0? So we take that expression we just found, that one, that cleaned up version, everywhere that's an h, we put a 0 in there, and now we're left with one final answer, negative 32x plus 80. And that is the derivative. That's what we found right there. F prime of x equals negative 32x plus 80. So here's my original function right here. Using that big 4-step process, we have found the derivative right here. Oh, they have derivative. That's the derivative of f at x is f prime of x equals negative 32x plus 80. It's going to be another function. Sometimes it'll be a worse, uglier, more complicated function. Sometimes it'll be something kind of basic like this, but you're going to get a new function. Is what's happening when you take the derivative. All right, and the last part here is the non-existence of the derivative. Sometimes the derivative doesn't exist, okay? And what happens is, if the limit does not exist at x equals a, we just say the function's not differentiable. Now what that means is, go back. See the example we found right here? This is going to have a domain. If there's any x's that you cannot have, that's the place that they're talking about when they say x equals a. They're just saying at these x's that may not be in the domain, that's where your function is not differentiable. Okay, and we'll talk about that in the next section, what it means when something's not differentiable. It means you can't do some of the tricks and some of the techniques we're going to do next, but there's still other ideas, other things that can happen here. Okay, so that being said, let's get into our homework problems. So remember from last time, we went through a majority of homework number 4, and I'll continue right in there. And like always, I'll just try to do these every 4 problems. And this is what we have. Okay, so we are now on number, what did I say that was? Number 35, trying to figure out. Okay, so we have find the slope of the line that goes through the given points. Now, this one right here, I don't need to spend too much time on this one, but it's a good problem to make sure you guys haven't forgotten this. And also why it's good is, remember, I kept writing this on the screen earlier. Your formula that you're doing, that instantaneous speed, that average, the slope, the derivative, they're based on this formula right here. So that's why it's a good idea. Just remember, you got to call one of these 1 and one of these 2, 0.1 and 0.2. And the only thing people get wrong on this one is they forget to use parentheses, which means sometimes they get the wrong sign when they should be adding instead of subtracting, or vice versa. So in this case, we're subtracting that negative 11. We get negative 4 minus 12 all over 10 plus 11. That looks like negative 16 over 21. I'm doing that kind of quick, so I hope I'm okay on that one. So the slope is defined. I'm getting negative 16 over 21, and we're good. So that's how we're, just like I said, just a couple problems to refresh your memory on what it means when you're finding the slope of a line given the 2 points. You're going to get a couple of those, but most of them, no. Some of these are review, like I said, just to kind of help you remember what you had learned before. So now we have rationalizing. Now I'll go back a problem because I saw the same thing. When you get a rationalization, and I'll go back to that number 39 in a second. When you're rationalizing, remember the rule. You don't want to have a fraction inside of a square root, and you don't want to have a square root on the bottom. So when you have a square root on the bottom like this, the solution is I just need to go and multiply the top and bottom by that root. And I get a 3 root 5 on top, and on the bottom I get a root 5 times a root 5, which is just a 5, and that would be my answer. Okay, so I have a 3 root 5 divided by 5. Now notice the 3's in front. It should still work, but if it doesn't, I could have redone it and put the 3 up on top next to that, but it does work in this case. So that was the basic approach when you're rationalizing when there's just a single root on the bottom. However, when you have 2 terms on the bottom, there's still a root on the bottom, so we still have a problem, but what I want to do now is I want to get rid of this. You can't just multiply by a root 7, because what happens is that'll fix the root 7, but the 5 is going to get multiplied by it, and it's going to cause another problem. So when there's 2 terms, we have to multiply by this thing called the conjugate. I'm sure that word is going to be is familiar to most of you. You've heard of that at some point. You wouldn't be this far if you had never heard of it. But remember, the conjugate is the same thing as the denominator, except you change the sign in the middle. 5 plus root 7, the conjugate is 5 minus root 7. If this was a 9 minus root 3, my conjugate would be 9 plus root 3. You just change the sign whether it's plus or minus. And now we FOIL out. On the top, now remember this rule here. I'll give you a little trick I love to show people. Whenever you're multiplying some roots, there's always a concern of what goes where. I call it the inside-outside rule. Whatever was on the outside of the root, it stays on the outside and multiplies together. Whatever was on the inside stays there, and those multiply together, and that's it. Nothing should be jumping in or out of the square root when you're multiplying it out. So keep that in mind as we're doing this. As I FOIL, I get 3 times 5. Well, that's easy. That's just 15. Okay. Then I get 3 times negative root 7. Well, the negative is outside the root. The 3 is outside the root. The 7 is there. So that's my result from FOILing those. I do the FOILing. Okay, doing the inside. We get 5 on the outside, 7 on the inside, and there's a positive, so that's going to be a 5 root 7. And the last, we have a negative times a positive. That's a negative. And both those numbers, they multiply together inside. They're both inside, so you multiply them inside. That's where the 49 comes from. Okay, and I do the same thing on the bottom. I get a 25. I get a minus 5 root 7. I get a positive 5 root 7. And I get a minus square root of 49, very similar to the top. Now, what you should notice is, this is why we pick the conjugate. There's something, I'm going to look at the bottom only. This will always happen where on the bottom, the middle terms cancel off because of it being the conjugate. It's like the difference of two squares. That's why we pick the conjugate, is because it forces the bottom middle numbers to cancel off, and that's why we're left with just non-square roots. Remember, that was our goal, get rid of the square roots on the bottom. Yeah, we're going to get square roots on the top, but that's okay. So, on the top, remember, the middle two terms on the top, they're both similar because they both have the same square root. If one's a root 7, one's a root 12, you can't combine them. You can't do anything with them. But when they're both the same square root, you treat them like x's. That's like me having a negative 3x plus 5x, I get a 2x. In this case, I get a 2 root 7 when I add, subtract things. When you multiply or divide, it's doing this rule. When you're adding, it's all about similar terms, and the root doesn't change. And then last, we get a minus 7 up top. And then we just have to keep simplifying this. Add numbers together, add roots together. Well, there's no more roots on the top, so it's just a 2 root 7. And the 15 and the 7 combined, they become, 15 minus 7 becomes an 8. Same thing on the bottom, we get an 18. Now at this point, if you're going to simplify, always try to simplify. And they tell you that right there. Always simplify. So we're not quite done. The rule is, if I want to divide something away, it's got to be like the inside-outside rule. I can divide things that are on the outside, or I can divide things that are on the inside. And here's the kicker. It's got to be for every term. So on the top, I got a term there, I have a term there, I have a term here. So if I'm going to cancel anything, it's got to come from all three terms, and it has to come from the outside, is usually what the case is. And sure enough, this 8, this 2, this 18, I can divide them all by 2. So my final answer is going to be 4 plus, the 2 is gone, so it's just a 1 root 7 or just root 7, and the bottom is a 9. Now I did that kind of quick, so I hope my math is all correct on there. So we're going to get a fraction. We have a 4 plus root 7 all over 9, I think. And there's our answer. So again, pause this, look it over, look at every step I'm doing, make sure you understand it before, we go on to the next part. Like I said, you can always pause the video and we can come back later. Or you can resume later is what I mean to say. Okay, so let's look at number 43. For f of x equals x cubed, the instantaneous rate of change known to be 12 at x equals 2. Find the equation of the tangent line to the graph at the point with x coordinate 2. Okay, so here's what's going on. Remember, when you see instantaneous rate of change, that's like your derivative. That is basically the slope. Slope of the tangent line. Okay, you remember that graph we had earlier? I can't remember how it looked, something like this. And we found 2 points, and we found the rate of change in between them. Well, that was the slope of the line. Well, that was when you have 2 points. When they're only giving you 1 point, your instantaneous rate of change is the slope of this tangent line right here at the point they're talking about. So you don't need to graph a picture. You don't need to draw the picture, but just, for our purposes, I'll kind of show you what they're talking about right here. So let's look at our graph, and if you forget how y equals x cubed looks like, it kind of looks like this and like that. So what they're saying is here at x equals 2, the rate of change is 12. That's the slope of that tangent line. That's what they're saying. They don't just come out and say it. But that's what you have to understand. When they say instantaneous rate of change, you got to say to yourself, oh yeah, that means 12. That's my slope. So what they want is, they want to know what's the equation of the line. This black line that I have right here. Well, think about it. There's two ways to get equations of a line. And this is something that you knew, but I want to remind you a little bit. Okay, sorry if that's messy. Okay, two ways to find the equation of a line. We have the y equals mx plus b, or we have the y minus y1 equals m times x minus x1. Your slope-intercept form on the left, your point-slope form on the right. So let's keep this in mind. Every time you are told to find the equation of a line, they want one of these two things that I just wrote down. You have to give me an equation of a line. Like y equals 1/2 x minus 7, that's an equation of a line. They're going to give you hints on how to find it. So remember this. In order to use this formula, if we want to get, okay, this is what we want. We want an equation of a line. In order to use this first one, we need the slope and we need the y-intercept. In order to use this other equation, we need the slope and any point. Now keep in mind, these are points on the line. The slope-intercept of the line, not of the function. Okay, I'm not talking about this. This is not the y-intercept. It's the y-intercept down here of the equation of a line. So right now, all I'm focusing on is this line. This is all that matters. I need to find the equation of this line. Okay, well, how do I do that? I need to get the slope first. Well, guess what? I have the slope. I know that, so I'm okay. I know it's 12. I know it's 12. So at least I can use either of these equations at the moment. Now the question is, do we know the the y-intercept? Unfortunately, we do not. It's not given to us, so that's not the one I'm going to use. I'm going to use this other one that has any point. Well, look at that equation of a line. I do know that point right there. It's 2 comma something. Well, how do you find it? Well, remember the definition of a tangent line is it's touching your graph at exactly one point. It's touching at this point right here. So what I'm going to do is I'm going to go to that function that was given. You plug the 2 in there, and that tells you the coordinate is 2 comma 8. That again is of this function, but your tangent line shares that point with your function. That's why we plugged it in, so that we can find the point. We use the function to tell us the point. So now I should have enough information. I have my point 2 comma 8. Okay? So I'm going to get rid of this side because we didn't use it. I'm going to go to business here with that formula, that point slope form. I want to go and find the equation of a line. Well, y minus the y value right here, this 8 equals 12 from the slope times x minus 2. And then now we just have to clean this up a little bit. 12x minus 24. Bring the 8 over, we get 12x minus 16. That's the equation of this black line, this tangent line right here. That's what we have found. Okay? Any questions on that? Think about it. Email me, obviously. We're not in class. You can't tell me right now. But think about it. Make sure you understand how this works. Now I'm going to plug in the tangent line. Y equals 12x minus 16. And there's our answer for number 43. So again, pause it. Look at it. If you have any questions, shoot me an email. But check this over. I want to make sure you understand how I went through this entire process. And don't forget, sometimes they're going to say, what's the slope of the tangent line? Well, we already got it. It's 12. Sometimes they're going to say, give me another point. Sometimes they're going to say whatever. They want the equation. So as soon as you hear equation, I want you to think y equals mx plus b, or this form, the point slope form that I put up. Okay, and just so we're clear, I'm sorry about this. This point slope form, that's y minus y1 equals m times x minus x1. You use the points from that point 28, you use the slope of 12, you plug them all in, and you get your answer. Okay, so again, pause it, look it over. When you're good, go ahead and resume the video, and you can look at our next problem that we're going to do. Okay, so number 47. We're going to have multiple parts, but this is good. We can do this. Okay, use the four-step process to find f prime of x. And remember, f prime of x is the derivative. Okay, so they want the 4 steps. So, and it looks like they just want the final answer. Oh, okay. Find the derivative, that's what's going here. Then find f prime of 0, f prime of 6, f prime of 8. So I'll show you how we do that first. So remember the 4-step process. Number 1, find f of x plus h. So I take this function, and everywhere I have an x, I replace it with a parenthesis x plus h. So see that original function right there. The 3 is there, the -5 is there times x plus h, and the 2 parentheses squared. So f of x plus h. Going to FOIL this out. And remember how I said earlier, you're going to be FOILing out x plus h a lot, so you're really going to get to know this. That's how I knew that was the answer. And then I'm just going to keep cleaning this up as best as I can. 2x squared plus 4 xh plus 2h squared. Notice I distributed the 2. That's what I'm doing right there. Then all of this stays the same. And if you can, simplify, but usually you cannot at this point, and that's just 6 terms. Okay? So the second piece is we're going to find f of x plus h minus f of x. So I take everything from right above. And then I'm going to subtract the original function right here. Now, I know I'm running out of room, so I'm going to squeeze this in here. This is the original function. 2x squared minus 5x plus 3. Okay, a little tight, but we'll make it better here in a second. So this is what we're calculating right now, the second step, f of x plus h minus f of x minus the original function. So I have a 2x squared plus a 4xh plus a 2h squared minus a 5x minus a 5h plus a 3, and then distribute the negative. Now, a lot of you are probably wondering, could I have just gone to this step? Did I have to write the whole thing just to distribute a negative? The answer is no. If you're able to do the negative distribution up here in your head, that's fine. You don't need to write every single bit here. So now remember what happens is things should be canceling. All right? The 2x squared is going with the negative 2x squared. The negative 5x goes with the 5x. The 3 goes with the negative 3. And we're left with a lot less. We have a 4xh plus a 2h squared minus a 5h. And that's it for that second step. Okay? Now the third step is you're going to take everything that we found, f of x plus h minus f of x, and we're dividing it by h. Okay, so that would be all of this, 4xh plus 2h squared minus 5h all over h. Remember, like I did earlier with the square roots, how many terms do you have on top? Well, I've got these 3 terms here, 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 and I've got this h on the bottom. As long as you cancel from every one of these terms, which is what we're going to do, we're going to cancel one h from every one of those terms. What we're left with is a 4x plus 2h minus 5. Okay, now I know I'm out of room here, so I'm going to jump up here and try this. Last step is find the limit as h approaches 0 of what we just found. 4x plus 2h minus 5. And all that is simply replacing the h with a 0. As soon as this h over here cancels off, now you can replace every h with a 0, and that means your middle term is going to drop off, and this is my answer right here. That is my derivative. So that's what I'm going to plug in here first. 4x minus 5, and there's our first correct answer. Okay, so again, pause this, and then I'm gonna, if you need to look at more, because I'm gonna clear the whole screen out right now. Okay, we have our answer that we care about. Now they want you to find f prime of 0, and remember, we have f prime of x right here. We just found it. So if somebody asks you what's f prime of 0, you go to the f prime, the derivative equation, and you plug in 0 for x, and that is telling you you have a -5. And then we're going to do the same thing with f prime of 6. We go to that same function, 4 times 6 minus 5. Looks like it's 24 minus 5. We get a 19. There's the result of that one. And last, f prime of 8. 4 times 8 minus 5. 32 minus 5 gives me, I think, a 27. And we are good on that one. Okay? So again, let me go back. Pause it if you need to see it, but the last three are easy. It's the hard part is that first one. Getting the derivative is a difficult part, but once you have it, now you can find the derivative of any x you want. Any single one of these, you can do that. All right, so let's look at number 51, see what we got over here. Okay, use the four-step process to find this derivative. So you see the theme here. We're going to do this a lot. And this one I'm going to show you there's going to be a little bit of trickery on this one. F of x plus h means take your original function. Everywhere you see an x, you put an x plus h. So that's it for the first step. That's the good news. We don't have to do anything. Remember, you cannot distribute the negative or the 7 because a 7 is outside. It never goes to the inside of a root. You just leave it this way. Okay? Second step is f of x plus h minus f of x. So we take the thing we just found and we subtract the original function. That's going to give me 4 plus, sorry, let's fix this. That should be 7 times x plus h. So 4 plus 7 root x plus h minus 4 minus 7 root x. The 4's cancel off, so we actually just have 7 root x plus h minus 7 root of x. That's it for step 2. Okay. Step 3 now is where it gets kind of interesting, okay, to say the least. Step 3 is where you're going to take everything we just found and we're going to plug that in over an h. Now the problem we had earlier was we were able to cancel the h no problem because of the way things worked out. But here, when you have roots, things don't cancel the same way. There is no way to get rid of this except we're going to do what we did earlier. I'm going to multiply by the conjugate of the top this time. And I'm going to do that on the top and the bottom. Now remember, we did this a few minutes ago to get rid of the roots on the bottom. We're not trying to rationalize this time. We're trying to make that h go away. Now, it looks like we're going to make life pretty difficult and worse, but you'll see it won't be as bad here. Okay, so watch what happens step by step on the top and the bottom. So I'm going to erase a little bit of this previous one. You can always rewind the video if you need to go back and see where I got that from. Okay, so I'm going to look at just the stuff that I'm multiplying on the top and the bottom. It's again a FOIL problem on the top. Okay, so watch what happens. On the top, we're multiplying this times this. So I get a 49. I get a root of x plus h squared because they're both x plus h, which is going to be nice in a couple of seconds. Outer terms, we get a 7 times a 7, so that's a 49. And we have a root of these two things multiplied together. So if I multiply x plus h times x, I got this. Or I can multiply it out and get x squared plus xh. It doesn't matter. What matters is when we do the inner term, we have a 49 with the exact same thing. Remember, that's the point of the conjugate is you want to go and have the middle terms cancel off. Okay, so let me fix one thing here real quick. So just moving this over a little bit here so we have more room. So now I foil the doing the very last multiplications. I get a minus 49 square root of x squared. Notice I kept with that same rule, the inside-outside. The things that are outside, the 7s, they multiply together and make it a 49. The things that are on the inside, they multiply together and become various things here. Okay? Now on the bottom, all I have is an h times, and I'll go ahead and multiply this out. Let's do that. Remember, outside things, they stay outside. Inside things stay inside. So what happens next is, in this first term right here, I have a 49, and the root and the square cancel, so I have just an x plus h. In the next term, the next two terms I should say, you'll see that these are identical because it was the difference of two squares, because it was the conjugate, they're always going to cancel off. And last we get this minus 49x for that. Okay. So now we want to clean this up a little bit more on the bottom. Oh, sorry. I have a 7h. And what I realize what probably would have been better is to leave this thing factored, but it's not going to matter too much. So I'm going to go back and refactor it. So from this line right here, I just factored out a 7h since they both have a 7h, and I left the two roots in the parenthesis. It was the same thing that we had up top here. It's like if I left the h and I pulled the 7 out, I would have this. It doesn't make a huge difference, but it's just an alternate plan. Now on the top, I have a 49x plus a 49h minus a 49x. And I'm going to clean that up before I do the bottom, just to save a little bit of time. These cancel. All I have is a 49h over all of this. Now, hopefully you've realized, if not already, these problems are going to take up a lot of space. Okay? So give yourself room. I have a small screen, and I have to keep erasing, but use your paper. Don't use it sparingly. Spread it out. Now, the only thing left to do is these h's are finally going to cancel off. And that's kind of your ultimate goal. I need the one single h on the bottom to be gone, and it is. In fact, the 7 and the 49 will cancel as well to make it a 7 up there. So my final answer for part 3 ends up being 7 over root x plus h plus root x. All right, and your last fourth step is we want to find the limit as h, let's do this again. A little bit neater. We're going to find the limit as h approaches 0 of the function that we just found. Okay, so again, pause your screen if you need to review this anymore. Then I'm going to just now remove everything just to give me some more room to finish writing out the part that we need to do, part 4 on this. So we have some expression. We found the f of x plus h minus the f of x. We divided it by h. And after all this ugly work, we got it to cancel off. And now we have one expression where we say, well, what is that expression as h approaches 0? And now all it takes is, even though there's an h on the bottom, I can still plug in a 0. I get 7 over root x plus 0 plus root x. That's 7 over 2 root x. Okay? That right there is your derivative. That ugly thing that we found, that's what we're going to plug in here after doing all these steps. Now the good news is in the next chapter. We're going to learn a better way to do this. It's even faster, but you need to understand this way first before you can do anything else. Okay, so our derivative is correct. Now we have it correct. I'm just going to start plugging in numbers. Some of these you can do easily. This is my derivative. I want to find f prime of 1. I replace x with 1. That just gives me a 7/2. F of 2, I'm going to put in the 2 right here, so the 2 is not going to go away, so I'm going to get 7/2 root 2. No calculator. Notice they say exact answer using radicals. Don't use any kind of a decimal, no calculator when they say an exact answer. And the last one, f prime of 3, you can kind of guess where it's going to go. You get a 7/2 root of 3. And there we go. Okay, so that was it for number 51. Let's see what 55 is all about. Oh yeah, let's discuss the validity of this following statement. If it's always true, explain why. If not, give a counterexample. The average rate of change of a function from x equals a to x equals a plus h is less than the instantaneous rate of change at x equals a plus h over 2. All right. Now, some of these, I'm going to admit, I don't always like how these are worded, so don't worry too much if you're having trouble with them. I don't like to give these on the test because they don't really show me a whole lot. I like to have you work everything out. But when you look at what's going on here, a plus h over 2. So if I show you a picture, let's do this. Okay? We've got some curve going on like this, whatever it is. Here's the a. Here's the h amount in between. So this is a plus h, your end result. And what they're saying is, what's the rate of change between them? Okay, so that's the average rate of change right there. Then they're wondering if h over 2 is basically the dead center. So in each case, instantaneous rate of change is a slope of the tangent line. The average rate of change is the slope of the secant line. Okay, so remember how slopes work. Here's my secant line. Here's my other one right there. In this case, this slope right here is definitely going to be bigger. Okay, but that's just how I drew my picture. If I had done this, excuse me, in a different location, we would have gotten a different result. Show you what I mean. If I said, let's make this over here be a plus h, okay, this is a little more obvious. This is the slope, the average rate of change there. But in the middle, it might have a tangent line like that. And you can see this is definitely going to be a lower slope than this one. So in this case, it's not going to be less. This is a case right here where our slope is actually going to be bigger. So that's one example where it's false. But in general, you really can't tell by what's in the middle. This has to do with the example I told you. When you're driving down the highway, your average rate of change is your average speed. They take your entire distance traveled over the entire distance it took, or the time it took. And in between, there are stretches where you're going faster or slower. This problem is talking about right in the dead center of your trip. So if this is like a 100-mile trip, they're talking about, what about right at the the 50-mile mark, or right at the 1 hour mark? Was your speed higher or lower? There is no conclusion. It could have been either. So what it's saying is here, looking at my examples, it's not a true statement. See, average rate of change. I want to read them. Yeah, and this is the tough part of these. You got to read them all and make sure. Okay. So it does approach it, but it doesn't mean it's always going to be greater. False because a car could drive at an average speed of 40 over it, but could be driving 45 at that moment. And then I'm going to jump to the last one. Oh, sorry. The instantaneous rate is not always going to be less. The last example almost says the same thing, but it's not quite. So make sure, let's look at B here. It's kind of the example that I stated, but average speed at 40 miles an hour from this area right here. Okay, so the span could be 45, but it's driving 45 at the middle, 40 and 45, this is actually kind of proving what it says right here. Okay, because they're saying the average rate is less than the instantaneous rate. If these are backwards, it would be this would be the correct answer, but they've got them reversed. They actually listed it actually is less than. So it's not false because of that. Okay, average rate of change, if the average rate of change is 20, the instantaneous rate of change over there could be a plus 10. I don't know if I like that one either. And you see why I don't actually like these on a test here. They're good for practice, but I know they can frustrate some of you, so I don't want you to get wrapped up on these problems too much. Okay, so if we have to pick, just looking at everything here in the problem, yeah, and it really does, it's going to depend on what graph you have, what function you have. I want to make sure I didn't miss any reading here. Okay. So I'm going to play a little game here. I don't like, I'll tell you, I don't like either of the false answers. I have a suspicion they might have made a mistake. If that's the case, I'm going to tell you guys just to skip number 55 when you get there. But let me see if they give an explanation of this. It's not this one. It's definitely not this one because they have it backwards, but I have a feeling they might have accidentally done it. Yeah. Okay. So their example, they just mixed the two numbers up, quite honestly. It was the same example I used. The average speed is 40, which is what this part was right here. The average rate of change was 40, is less than. Bottom line, here's what I want you guys to understand. There is no connection between what happens in the middle and what happens to an average rate of change. Because, use my example of the car, you can have the average speed of 40, but in the middle, you could be 45, you could be 35, you could be 10, you could be 90. And this example was talking about the actual speed right in the dead center of your trip. Well, that has nothing to do with your problem because I could be going fast at that one moment and then slow the rest, or I could be going slow at that moment and fast at the rest. So, like I said, I don't want you guys to get too wrapped up on number 55. I'm not going to put it on your quiz. If you get stuck or you have any questions, just let me know. But don't worry too much because this is not the kind of problem that I like to ask you very much, this 55. It doesn't show me what you actually know. This one, however, will tell me a little bit more. One of our revenue problems, and it's very similar to the one that we did earlier. This is talking about car seats, and it's saying this is the revenue function when you go between 0 and 3,200 seats made. Find the average rate of change in production from 1,000 to 1050. So remember how the average rate of change goes in this one. Okay, so average rate of change, the formula is, let's find f of 1050, what we finished with, subtract what we started with, and correction, it should be the revenue function, not the f. I'm just used to writing f, but the r function, the revenue of each, and then on the bottom we go with the 1050 minus the 1,000. Okay, so it's going to require us to plug in the 1,050 into here. Okay, so let me cheat and get my calculator out a little bit just so we can do this a little faster. Don't want to waste any more of your time. So we're going to do 64 times the 1050 minus 0.20 times the 1050 squared. So R of 1050 equals 64 times 1050 minus 0.02 times 1050 squared. Okay? So This gives us our 67,200. And then we're going to take 1050, square it, and then multiply it by 0.02. We get 22,050. So I'm going to make that a subtraction and add the 67.2. And that gives me a 45,000. Yeah, that's right. 45,150. And on the bottom, of course, it's just 50. I don't need a calculator for that. So I'm just going to take that number, divide it by 50, and I get 903. Okay. I'm hoping I typed everything in correct. It didn't seem like the right number for me. I have a feeling this is going to be wrong, but we're going to learn from this. Okay. I must have done some of the math wrong here. Oh, I know what I did. Sorry. Let's go back. I know exactly what I did wrong. We found R of 1050, which is this 40,150. I hope that was what I had just now. Okay, 45,150. We still need to find the R of 1,000 right here. So I have to do this one as well. I forgot about the second half. That's why everything seemed very high to make a profit of $903 per car seat. I know there's some car seats that are expensive, but not that many. So we have the 64 times the 1,000 minus the 0.02 times 1,000 squared. Okay, so this is going to be 64,000 minus 1,000 squared times 0.02. That's my 20,000. So at least there I can do that math. That's going to be a 44,000. So now we have this. Get rid of that 903. That was wrong. And this is where I always try to show you, use your common sense. If a number doesn't seem right, don't just believe it because your calculator said it. You got to use your common sense. Like I said, these problems, they try to make them as accurate as they can to a real life situation. So if you're looking at car seats and you're seeing a $903 profit, if you had kids, you know, well, they're not that much. So think about what sounds right. So we divide that by 50. Now we're at $23. Now I'm starting to feel a little better. That sounds like a number that we would get. I don't want to get too excited yet, but we're good. Okay. There it is for that. Now they want us to find the derivative. Okay, so again, pause the screen if you need to. Review this. Then I'm going to go and clear it all and start all over again to do the derivative. Okay. So remember the first step. We want to find R of x plus h. So that's going to be 64 times x plus h minus 0.02 times x plus h squared. 64x plus 64h minus 0.02 times the old x squared plus 2xh plus h squared. Okay, again, I'll say it. You're going to be squaring x plus h a lot. So get used to it. You will figure it out very quickly. Okay, so this next one's going to be minus 0.04 xh minus 0.02 h squared. Okay, so that's the R of x plus h. So what I'm going to do is, in time, you'll start going to this step immediately. I'm going to go and just find out, this is what I need to ultimately find. F of x plus h minus f of x all over h. Okay, so that's what we need to find. So what I've got now, I've got the first component. I'm just going to go ahead and put that in right now. So on top, I have the 64x plus the 64h minus the 0.02x squared minus the 0.04x h minus the 0.02h squared. So that's everything I found for just the f of x plus h right there. Okay, so I'm going to clear all this out since we've moved it, the stuff that I just wrote in black. Now on top, we still have to do more. We have to subtract the original function, that minus f of x. So that's what's going here. And remember, it's just copying the original function, but we do a subtraction. That's all we have to do. So let's try a different color on this one. For this right here, it's a minus, and it's the entire function, 64x minus 0.02x squared. And all of that is over h. Okay, now I'm going to save a little bit of time. Remember, this is the negative 64x and a positive 0.02x squared. If everything went right, all the terms that don't have an h are going to cancel. 64x minus 64x. Negative 0.02x squared, positive 0.02x squared. Then, and like I said, as you do more of these, you are going to start to ask questions like, well, can I just do this now? Can I just cancel the h now? And the answer is yes. If you're seeing that, go ahead and cancel. So I'll move it up top here. When I cancel the h's, because now every term has an h, we're left with just 64 minus 0.04x minus 0.02h. Since it's the limit as h approaches 0, I just plug a 0 right in there, and all I'm left with is this. And keep in mind, you no longer write that limit symbol. The limit symbol is telling you, let's go and approach h to 0 or replace h with 0. The moment I plug in a 0 like I did right over here, that thing is gone. Okay, but until then, you need to keep the limit there. So as soon as I replace h with 0, now I just have my answer. I have my function, I have my derivative, and there it is, our 64 minus 0.04x. There's our derivative. So again, pause that if you need to look this over. I'm going to clear everything out. All right, now we got to plug in 1,000, and this should be a little bit easier because now we have this. Our function is a much smaller function. I just have to replace 1,000 and multiply it by 0.04. I'm looking right at the step we just did. And that's a negative, so I subtract that from 64, and I get a 24. Oh, what in the world did I do here? Okay, try it again one more time. Sorry about that, everyone. Okay, 0.04 times 1,000. Oh, okay. See if anybody caught my error. They're not asking for r prime. They're asking for r of 1,000. Okay, so we already did this earlier. What's r of 1,000? We got to go to this original function right here and plug 1,000 into this function. So not the derivative, and it's a subtle difference. You'll probably make that mistake just like I did, so don't feel bad. 64x minus 0.02x squared. This is where I need to plug in the 1,000 to. 64 times 1,000 minus 0.02 times 1,000 squared. Okay, so try that calculator one more time. So we have 64,000 as my first piece. We have 1,000 squared times the 0.02, and that's a negative 20,000. So that was my 44,000. And hopefully, there we go. Okay. Then they want us to find the derivative. Is that the 24 that we found earlier? Now we plug the x into this function, and that was a 24 we found. And then we have to interpret these results. Okay? This means the production level, at a production level of 1,000 car seats, the revenue is that many dollars, $44,000, and is increasing at a rate of $1,000 per car seat. R prime dollars per car seat. Now remember, R prime is the slope, how fast it's rising. So that first one sounds good. Okay? This one is 1,000 car seats making this many dollars, which is always true, and it's decreasing at that rate. Well, if this value that we had right here for R prime, if that's decreasing, that means production's going down, revenue's going down, so then it would be decreasing. But it's not a negative, it's a positive 24. So remember, this is telling you the slope at that exact moment of 1,000, it's going up at a rate of 24. The last one is production level 1,000 car seats, the revenue is R prime. Well, it's not $24 because this is, again, how fast it's going up. So you have to distinguish them. The derivative, the prime is telling you the speed, how fast it's going upward. The R by itself is telling you the actual dollars. So A looks like our best guess, and there we are right there. Okay, so that looks like we got to the end of everything that was in this assignment. The first few problems you're going to see in your homework are going to be fairly simple and straightforward. Then as you get to these last 8 or 9, yeah, they're going to have some extra, complicated parts to them. So just want to show you where we're at. Yeah, so we've kind of done all these. We've covered them all. Again, if you have any questions, feel free to reach out to me, shoot me an email. Other than that, you should be good to go with everything in this this week 4, homework number 4 right here. And then, of course, like always, get ready for the quiz. But we're ready. You should have everything that you need for these problems here. Okay? So I'll post this video. I'll post another one coming up for next week's. Like I said, I try to get those out on Sunday or Monday sometime. If you're ahead, though, and you have any questions, feel free to reach out to me. If you're ahead, it's never a bad thing. Just make sure you're worrying about your current stuff, your quiz, and your other assignments. Don't try to go ahead if you're having trouble. Okay? So have a good weekend, and I will talk to you all next week. Take care.